Hello, everyone. Do you hear me?
Yes.
Okay, so let's have our last lecture of this course, and this is going to be about unsupervised learning. Let me share screen 1 second. So. I think there is some problem with the Wi-Fi here today, and so please, if I disconnect from one of the two devices, just let me know by chat or something. So today is unsupervised learning. Okay, so far we have dealt with supervised learning, where you have some data, you have some input, and also you have some output. So this can be your regression or your labels in a classification or something. So in contrast, so this is supervised learning. In contrast here, in unsupervised learning, what we have is just a bunch of points, which can be which can be not, which are unlabeled, in a sense that typically you can picture this as some clouds of points where a priori there is no apparent distinction between them, right? So there are, as I was saying, probably in the very first lecture of overview, there are like questions that unsupervised learning try to answer. So first question is, so some questions addressed by unsupervised learning. So first question would be, can data be separated? In clusters? Like maybe this is a cluster and this is another cluster. And that would be like the analogous to classification, right? But just try to see whether there is some feature that allow you to separate this data somehow, to clusterize it. Another question was, does data live in a lower dimensional space? For example, imagine you have these 2 dimensions, and then you have your data points like this, right? So essentially, you would say that, okay, maybe this is essentially a one-dimensional data. I mean, you lose some information by reducing dimension, but essentially all the information is contained in this direction here. And the other question was, so what is the underlying distribution, right? The underlying distribution of the data, or the distribution that generated this data. This was this was answered in the in this lecture about non-parametric methods. If you remember, we had these ansatz for the distribution of the data, like this, and either kernel methods or nearest neighbors, let's say. So we have partially covered some of the questions that are posed in unsupervised learning. And so today we are trying to address this one. We're trying to study this one here. And hopefully I will have time also to cover dimensionality reduction. So this is today. All right, so let us start with clustering, which is the first type of unsupervised learning task. So again, here the idea is to have something like this, right? So let me just pick this figure and put it in the next page. So intuitively, we think of a cluster as comprising a group of data points whose, let's say, whose distances, interpoint distances, are small compared to the distance between a point here and a point here, right? So this is more or less the idea of grouping according to distance. So use intuitively, right? The idea is to group according to some measure of distance. And the simplest probably algorithm for achieving this is so-called k-means algorithm. Which I describe next. So the very first thing we do is to let's take number of clusters k to be fixed. So this is given, and then what you do, so you have your data set, your unlabeled data set here on 1 to n. So, and then you build, if you want, for each data set, for each point in your data set, you build some vector, some binary vector, I, which is just RI1, RI2, RIK. So which is if you want, this is called an indicator vector. This is a binary vector. And this is somehow telling you about membership, right? So which cluster this data point belongs to. This is just a measure of. So for example, if you have k equal 3 and Ri is just 0, 1, 0, it means that point I is assigned to cluster number 2 or so. So this is the idea behind this. So note that, I mean, this is the way I have built this is like a one-hot encoding scheme or 1-to-k scheme. So this is similar to a multi-class classification problem. So it's the same way of parameterizing the labels. I'm just trying to get the memberships here, which I don't know a priori. So once I have this,
can I
yes,
ask a question?
Yes.
If we don't know anything about the data, how can we determine the number of clusters?
Okay, good question. So there are several things, several like recipes in the literature for determining a figure of merit for a given value of number of clusters. So the idea is that you repeat this exercise I wanted to describe to you for many values of k, many values of number of clusters, and then you decide which is the best value of k according to some criterion. Unfortunately, this is an unsupervised learning task, and there is no ultimate, or if you want, not ultimate, but there is no like a objective way of evaluating which is the best, what is the best number of clusters, let's say. But there are measures of that in the literature. Yeah.
Okay, thank you.
So I'm trying to think about an example, but the example I was thinking about is false, because I was thinking that you are in the context of collider physics, and then you want to study a jet, and then a jet has substructure, and so you want to see what is the substructure of these jets. So in other words, how many subjets you have inside that jet. But then I was thinking, okay, then I will use the fact that I know because of simulation, right? What is the true answer? But of course, when you go to real data, and then when you go to real data, this is no longer the case. I mean, in the sense, for example, if you are in simulation world, then you know that if a jet came from I don't know, a top, right? Then you know more or less how many. So you know this is bottom W. So you may have like 3 jets inside the big fat jet, top jet, or something like that. And then 3 will be your favorite value, but essentially you don't know what is the origin of that jet. So it is difficult. It is a difficult question, and I think that there is no like a unique answer to that. It depends on the problem. It depends on expert knowledge, and your intuition about it.
So we may know the number of clusters, but not the labels of what its data point, what in which cluster it can get. But we maybe know nothing also.
But we may, sorry, I lost this.
We may know the number of the clusters, but not
Yes.
the labels, or we may even not know any of this. You just need to optimize for the number of clusters also.
Yeah, exactly. Yes,
okay.
Yes.
I see.
Okay, so then once you have fixed your k here, and then you have this this way of quantifying membership here by this, then what the idea is to build something which is called the distortion measure. So the distortion measure is going to be at the end of your cost function, which is the following: RIK times xi minus mu k transpose the same. So this is a cost function to be minimized. Okay. Here, so here these quantities here from k equals 1 to capital K. So these are like these are like describing the centroids of centroid of centers of cluster K, let's say. So you have a d-dimensional space, and then there you will have like your this cluster is going to be, for example, described or defined by the centroid, which is this these vectors here, mu k. Okay, so then what we need to do is to minimize this distortion measure with respect to these values, and also these values. Okay. So if you look at this expression here, well, you want to minimize this with respect to, first task is to minimize this with respect to RIK. So obviously here, in order for this to be minimal, in order for this sum to be minimal, the best value of K would be the one for which these guys are minimum, right? So in other words, the value of K, the optimum value of K, is going to be the R min of well, let me put it like this, but you know that this is just a sorry, this is a transposed times itself, so this is just absolute value squared. It's just this term here. So obviously the best that you can do is to say, okay, I will essentially, a point xi is going to be assigned to the closest cluster centroid. Centroid, right? For all the points, right? And then you have this assignment. On the other hand, if I want to minimize now, let me now minimize with respect to mu k. This is easy expression because you see this is just analytical here. So the minimization of the derivative of this with respect to mu k, this is just 2 times this sum over the data points, RIK xi minus mu k. So I want this to be 0, and if I want this to be 0, the result is just so the two you can forget about it. So this is just this RIK xi RIK. So in other words, this mu k is just the mean of all the points assigned to cluster K. So note that here the denominator is just the number of points. I mean, this is just nk, which is the number of points assigned to K, because this is one for the points belonging to K and 0 for the rest of points. So this is an intuitive thing to do, right? So and then the procedure is sort of clear, it's straightforward, because given some first assignment of the clusters, centroid, then what you need to do is to assign the points to the cluster depending on the distance to the centroid, and then follow an iterative procedure that I will describe now. So iterative procedure to that. Of course, you need to start at some random position, some random initial position for the clusters, for the centroids of the clusters. Then once you have this, you find the assignment. For those given values of mu, and you update your guess for mu k with the previous assignment. And then you just repeat these steps until convergence, 2 and 3 until convergence. Okay, let me show you a picture of that. This is, I think this is at the book of Bishop. I don't see the picture now. Let me see. This one probably, yeah. So here, this is like this is a figure of the book. This is just the procedure here, where you have initially this clouds of points. They don't have any labels, so there is only one class here, so there is no class actually. So you first choose random positions for the two clusters, because you have fixed your number of clusters to be 2. So you just pick this random position. Then in the first step, what you do, given these centroids, you assign each of these points to one of these clusters, this one or this one. And of course, the result is this one, because you see those points here are blue because they are closer to the blue centroid, and those points here are red because they are closer to the red centroid. So once you have done this first assignment, then you go again and you say, okay, I will recompute now the centroids of the cluster. And then the centroid of the blue cluster is going to be the mean of these points, which is here. And the centroid of the red cluster is going to be the mean of this point, which is here. Now you proceed again, say, okay, once I have recomputed my centroids, then I do again the assignment. And the assignment is now shown in this plot. You see it. So now you see that there is a convergence here, right? So then you repeat again this procedure, and then finally you get a convergence where there is in the sense that the convergence, in the sense that the centroids, they don't move, essentially. They don't move anymore. Okay, is there any question on that?
So I am confused about something of the procedure, because essentially you're talking about the centroid. So I'm all the time imagining that you have sort of disks over the plane, but we never described anything about the radius. And at some point I thought that you should say, okay, I stop my algorithm here, but I see no stopping point in what you described. So how do you know when I mean, essentially when the centroid stops moving a significant distance or something?
Yeah. Yeah, this is what I was trying to say, that essentially if you don't see, or essentially, once the membership of all the points remain stable, then you are done.
Right, but let's say this, let me be politically incorrect, these Gibraltar points near 0, 0, that could be either blue or red, right? I mean, it could happen in some algorithm that your iterations start flipping them over and back and forth, and then you never end because you are trying to dispute these last pieces of territory.
Mm-hmm. Yes, I mean, of course.
So you should put a stopping criteria.
I mean, what I can tell you is that according to this algorithm, this membership remain stable after this last step.
Okay, good.
And also, you may wonder, okay, what if instead of starting here, I start, I don't know, here or something. So, but it is going to converge more or less to the same position. Okay, probably, as I was saying, I mean, there is some ambiguity here, and there is some 1 or 2 points there which will change membership. But actually, I think that this figure is chosen such that the two centroids are completely orthogonal. So it is like describing clouds of points like this, where the clouds of points are really lying in other directions. So probably this random position was chosen, was secretly chosen such that the convergence is not immediate, because of course, if I have centroids, so I may say, okay, let me just put a line here, and then this is all very visual, right? And then I just compute the mean here and mean here, then this is going to be my initial centroid guess. But if you don't do this, if you put centroids which are completely off the clouds of points, then you see that in a very small number of steps, you converge to something which is reasonable. Anyway, about the problem of some radius of the cluster, the model that we will discuss right now does address that. So in a way, it is a model that is giving better results, the one that I will show now. Okay, so this model is, let's say, in terms of robustness, it is a probabilistic model, and specifically, it's a mixture model, mixture of Gaussians in this case. Okay, so let's see how this works. So what we saw in k-means, that this idea was to something like make hard assignments. So in k-means, you do something like a hard assignment of the points to the cluster. And so the idea here is to go And instead of making hard assignments, you do probabilistic assignments. So you would have the probability for a point to belong to the cluster, to the blue cluster, and another probability to belong to the red cluster. But in particular, there is the initial assumption here is the following. So initial assumption is that I have my data that came from a mixture of distributions, or a mixture of Gaussians in this case. So I will have k components, k different Gaussians. And each of these Gaussians will have, of course, a centroid and a variance, a covariance matrix. So that's why this is called a mixture of Gaussian model. Right. Now, I have a data set. So my data set consists of n points, which means that the likelihood is, or let me call it let me just write the log likelihood. P of all these points, I will collect all these points in this capital X matrix. And this likelihood will depend on parameters. So will depend on all these coefficients here, one for each Gaussian. So all of these coefficients I will just collect in a vector pi. And each of these Gaussians will have mean and will have some covariance. And this is just the log of, the sum of the log of the previous expression. So this is just k1 to k, pi k, and your normal xi mu k sigma k. This is my likelihood here. And then the idea is just to say I can maximize now maximum likelihood estimate with respect to the parameters of the model, with respect to mu k, sigma k, and also the pi k, no? That would be the way to go. The problem here is that, so by looking at this expression, this is an expression which is the sum of a log, but the parameters I want to find, the optimum parameters I want to find are inside a sum here, and not a product. So I cannot, if you want, I cannot do this thing that the log of a product is just the sum of the log. And essentially, this means that this is very difficult in practical implementation. It's very difficult to optimize. And what I'm saying this is I'm thinking about techniques as, for example, in stochastic gradient descent that we have seen, where you know that you have in general a sum over some terms here, that you can just approximate this by just, if I differentiate this with respect to some parameter here, is being approximated by just one of the terms. This is a particular case of a mini batch optimization, is called, where you have only one term, but you can have a group of them, which is actually in the typical procedure nowadays. So you cannot do this game here of approximating the derivative of a quantity like this by this one, just because here you have this sum inside the log, and this is in practical implementation. This is very complicated to optimize. So there is a very nice idea in order to cope with this, which is the following. So the idea is to introduce some latent variables z, one for each point, zi1, zik, one for each data point, and they are actually analogous to the previous method of k-means, to the RIK that we saw in k-means, in the sense that they are actually giving you some sort of membership. But these are variables that they are latent, so you need to optimize over these variables at some point. Right? It is just a now in a probabilistic fashion, right? Probabilistic interpretation. Okay, so the way to go is the following. So we identify pi k is going to be the prior probability of zk before any observation. In other words, I'm saying that the probability of zk equal 1 is just to be pi k. Of course, you know that I mean I haven't told this before, but these pi k's, they are normalized, right? So they are coefficients smaller than 1, and the sum over all pi k is 1. So they are really interpreted as probabilities here. So now note again that this is a one-hot encoding parametrization of these variables. So I can really write what would be the distribution of this z latent variables. This is just like a categorical. This is a categorical distribution, or a generalized Bernoulli, or whatever you want to call it. In the same way that just a categorical variable as we saw in the very first day. So this is the first thing. The second thing is we identify. Yes, a question? No question. Okay. So we identify these distributions. Just remember that the initial model here is just a mixture of all these distributions here. So the second ingredient in this procedure is to identify this distribution as the conditional distribution given a particular value of k. So the probability of x given zk equal 1 is going to be given by this one. And if this is the case, then the probability of x given given set in general, not one component, but all the components, is just the multiplication of the above, right? So, and it is just k sigma k to the set k, right? So this is just a consequence. This expression here is just a consequence of this equality, in the sense that if now k is equal 2, then all the set k is going to be 0 except set 2, and it's going to give you exactly this equality. So I have, by introducing this latent variable, I'm now identifying the elements of my original model, how they relate to these latent variables, and in particular, I am able to write what is the conditional distribution of my data given these latent variables. So then I have a way to write the joint distribution of both observed and latent variable, which of course you know that it can be written like this. And it is just a multiplication between this term and this term here. They both involve exponent set k, so I just write this as product of pi k given my conditional. To the set k. And note that this joint actually has the correct property that if I marginalize this, if I marginalize this distribution over Z, I should get my original distribution. I should get this one. So I have introduced that latent variable. I am writing what is the joint distribution between the observed and the latent variable. So if I marginalize over the latent variable, I should get this original model here. So for example, let's do it like this. So imagine what I'm saying is that you should get this property. I am marginalizing over Z. So Z here is, of course, it is a categorical variable. So it is a sum, not an integral. And let me just show this with an example. So imagine I have k components, 3 components, sorry. If I have 3 components, then Z can be 3 vectors. So 1, 0, 0, 0, 1, 0, 0, 0, 1, let's say. So this is by just looking at this, I am summing, I'm taking this expression for every value of every possible value of Z. So this is going to be for the first possible Z, then here k equal 1, k equal 1, sorry. So the first point is just class 1, second point is class 2, third point is class 3. So by doing this, I just get P1, pi 1, this first Gaussian, plus pi 2, this second Gaussian, plus pi 3, the third Gaussian, which is what it should be. Okay. So this joint has the correct shape because when I marginalize over Z, I get the original model, probabilistic model, which is just a mixture of the Gaussian. So, but okay, what do we gain by doing all this thing? Okay, the gaining here is the following. So assume that for a second that you know the values of set ik. So if this is known, then I can maximize not my log, what was it? Not this, because this is difficult. This, at least I try to convince you that this is a difficult problem to maximize this. But I will try to maximize instead the joint. So if you see the joint, well, the joint is not a, let me write the joint in general for the complete data set. So the joint distribution of observed and latent for all the data set. Let me write it like this, because I wrote here only for a point, and I will write it now for the whole data set. So this is just capital letters now. This is just multiplication, because those points are assumed to be independent. And then the other multiplication. Okay. Then set ik. So then you see that that this is an object which is convenient to maximize, because it is like, for example, you remember the cross entropy. The cross entropy was something very similar to the log of an object like this one. In other words, for a classification problem, a multi-class classification problem, the likelihood was exactly a double product across all the points, across all the classes of some terms here. And here is exactly the same. So this is an object which is this is an object whose maximization is tractable. All right. Well, the problem here is that you don't know the set values. So, but how to know it? How to know these assignments? Because given these assignments, I can go and maximize this. So if you put in comparison with a typical classification problem, these guys here are the labels. If you remember correctly, the labels were here, so you knew the labels. Now you don't know the labels, but this is something that you can get from that you need to extract from the data. So at the end of the day, what we have done so far is to write exactly the same likelihood to maximize as for that supervised classification, multi-class classification problem, except for the fact that here, instead of being known labels here, I don't know these objects. So I need a way to estimate these objects before trying to maximize this. Okay, so what we can do actually, we can have the posterior of, we can compute this object. So what is the probability of set ik equal 1 given some observation? So imagine now that I have observed one point, xi. I can certainly compute what is this posterior. And this posterior is, let me just write the first step here. This is just the likelihood, given that set ik is 1, times the prior that set ik is 1, divided by the sum over j to k of the same thing. Sorry. I set ij equal 1, p set ij equal 1. I can compute this because all these objects I have, well, at least I have the numerator of that. The denominator is just a normalization, right? So you can identify the first term in the numerator as, or yeah, okay, let me put like this one, xi mu k sigma k. This is the likelihood. This is by construction what we said, right? That was the conditional that we were trying to build. And you can identify this prior as pi k. No, over all this sum. All right, so then I do have a way to given an observation to estimate at least not probably what is exactly the value of zik, so these assignments, but at least the probability for a given assignment. So in other words, let me just rewrite the whole thing as the following. So this like the posterior of all the set given all the x's, all the points, given some parameters. So the parameters with respect to which I need to optimize is going to be proportional, and let me now forget about the normalization, to this expression which is a multiplication of all the terms above. Xi mu k sigma k to the zik. Right, again from this it is, I can write this for a particular value of zik. If this is 1, then this exponent is 1, and then you get this value. Otherwise the zik is 0 and you get nothing. Okay, so now okay, probably let us stop here and then let's do a small break, and then I continue to specify this maximization procedure. Is there any question so far? Okay, if no questions, let us do a break and come back at 12:05. Okay.
Okay, see you.
Okay.
Thanks. Okay, let us continue if you want. You see my screen now? Yeah, I think you see my screen, right?
Yes.
Okay, so then the way to go is it's a particular case of some very very popular, or at least it was popular before, and now I think it's still popular. Algorithm for finding the maximum likelihood estimates, which is so-called expectation maximization algorithm. Expectation maximization algorithm. And this is like a generalization, if you want, of what we did for the procedure we did for k-means. So it's a generalization of same procedure for k-means. So there is a two-step iterative procedure that hopefully will find convergence at some point. And the idea is the following. The idea is that since maximizing this is tractable, if you knew the values of set k, since maximizing this is tractable, since you knew the value of set k, then what you do is to consider instead the expectation of the log of the joint the expectation with respect to the posterior that we have just written. Okay, so the way to go is the following. Imagine that you have an iterative procedure and in this iterative procedure, you first evaluate the posterior with respect to, let's say, the values of the parameters of the previous iteration. For example, I can even start with the random values of my parameters, and then I can just evaluate. Let me call this old values of the centroids of the clusters, the old values of the covariance matrices of the cluster, and the old values of the coefficients of my mixture of Gaussians. And then you evaluate the joint with respect to the values of the present iteration. In other words, well, the log actually of the joint Okay. Not the previous one, but the present one. Yes, right. And those are actually the values that you want to extract. But then what you can do, let me just call this all these parameters, I will call them capital theta or something. let me just collect all of these guys in a capital theta. So this is what I'm saying is that the new values of the parameters are going to be just the Rmax over the parameters of this expectation. Where the expectation, I don't know if I wrote it, probably I forgot to write it, but expectation is just sum over z of pzx log of pxz. All right, so this is more or less the idea, and this algorithm is proved to converge. So the steps are, first of all, choose initial values of your parameters. So let me put this all here, which are just the initial guess. Then you have the E step. Let me just evaluate P of Z with this initial choice, or for every iteration, the previous set of values, if you want. And finally, the M step, which is evaluate or guess, extract new by maximizing the previous expression, this expression here. And then, of course, check convergence. If not, repeat 2 and 3. Okay. Convergence here is what? Convergence here is, for example, I have I say that my parameters, they change by a little amount that I initially set, and then this will define my convergence criterion. So it may happen that you think that this is quite a complicated thing to do, but the whole complication came, if you recall, from the fact that I was telling you that this object here is difficult to optimize. And then we introduced these latent variables, and then we were able to re-express the whole optimization, or the object to optimize, instead of being a complicated object like this one, to an object which is familiar to us, because we knew it from classification, where here you have the labels instead of these latent variables. And it is because you don't have these labels here that you need to make this two-step iterative procedure where you just assume some values for the parameters, and then you estimate Z, and with this, if you know Z, then you can just maximize this again, etc. So let me just put the corresponding picture of this process for the mixture of Gaussians with exactly the same data set. Yeah, so this is the analogous picture to the one before with the k-means, But now this clustering task was done with the Gaussian mixture. So here, again, here, initial cloud of points, they are all unlabeled. And you start with 2 random Gaussians with given centroids and unit covariance matrix. So you just start with that. You just initialize the centroids to be random, for example, these positions, and you initialize the covariance matrix of each of them. This is just this. And what you do is, so you do sort of the you do this how do you call it, the probabilistic assignment, if you want. So you try to guess what is the probability for this point to be blue or to be red, and depending on this you see the color, right? Because points which are clearly blue, it means that they have a large probability for belonging to this cluster, and the same for points having a clear red color, and points having a like a very similar probabilities of belonging to either cluster. They are like purple, right, in the middle. So once you have your probabilistic assignments of your Z or your set, what you do is to then you can now have this joint here that I put above, and you just maximize the expected value of the joint, after which you get new positions, new covariance matrices for each of them, right? And new also new pi k that is not shown here. So this is after 1 cycle, after 2 cycles, 5 and 20 cycles, which was probably the point of convergence here. So this actually, I just thought we could compare the classification from this to the ones of k-means. Let me just see if I put, let me just for a second compare this figure with the one we got for k-means. Where was that? K-means here. Yeah, so that was for k-means. Now I was just trying to see whether there is a difference in the classification, and then you see that there is a small point here that changed. So now the point, this point here in k-means was blue, but now it is red. This small point here is red. So except for this point, except for a point, all of the other points were assigned to the same cluster as for the k-means algorithm. But of course, I mean, this is a quite easy data set where you see by eye that there is some degree of separation between these clouds of points and these clouds of points. So there is intuitively, these two algorithms, they should give very similar results, and this is what happened. Okay, so is there any question on that?
Then for this particular data set, it's better to use k-means, because here I see that you have to make 20 steps in order to reach convergence, and in the k-means algorithm, what number of steps was?
I think it was 5 or so. So indeed, in this data set is is faster. I think in general, k-means is faster. Well, in any case, it's faster because I mean all of these. So in k-means, you only need to. There is no, for example, estimation of the covariance matrices. Because I just care about the centroids. So in general, the k-means is faster, not only requiring sometimes less iteration or less cycles, but also each cycle is faster in k-means because here I need to estimate a lot of parameters. So imagine that I am in a high dimensional space here where D is large. So covariance matrix is a D by D object. Each of these elements of each covariance matrix for each cluster, I need to find the optimum. So it is a it's a slower method, but it is a method that is giving better results for more complicated data sets.
Okay.
Yeah. Any other question?
Yeah, Brian, is there a way of determining which is the best number of clusters in which we could divide the data here? Like comparing...
I think is the same answer as for the k-means.
Okay.
Yeah.
Okay. Thank you.
Yeah. There are many metrics in the literature that you can find that tell you tell you a way to estimate the optimum value of k, but I think they are all domain dependent. They depend on the data set. They depend on the domain. I don't know.
Okay. Yeah, because in this example is very, I mean, looking at the
clear.
image, you can see it. Yeah, but okay.
Yeah, it's clear. So I don't know. I was thinking, for example, if now I imagine I do this exercise with 3 classes. I'm just guessing here, but if I do it with 3 classes, then you will have a lot of purple points, well, points in between, right? So imagine that I have a 3rd class here, or I said, okay, indeed, this should be 1 class here, 1 class here, and there is a small class here, for example. And let the algorithm tell me what is the best centroid and what is the best shape for this 3rd Gaussian. But maybe the posterior distribution of these probabilistic assignments is actually smaller with 3 classes than with 2 classes. I'm guessing here, but it is really not a unique. There is really not a unique way to do it.
Okay.
Okay, so then that's all I wanted to say for clustering task. And now let me go to, in the last half an hour, let me just go to the other, probably not in full glory because it is maybe lengthy, but at least introduce the idea. So now let's describe a task of dimensionality reduction. This was another thing that another task which is addressed by unsupervised learning, and the one of the easiest algorithms to do that is called principal component analysis. Okay. So the idea here is to extract from data some like underlying features that explain grosso modo, right, the whole data set. So just put here again the cloud of points. So if you have a cloud of points which is clearly correlated, so then you may say, okay, probably this single dimension explains most of the data. So if you have a data set living in D dimensions, sorry, what did I do? Xi, where the dimension of X is D. So then the idea is to define a transformation of the data set to a lower dimensional parameter, to a lower dimensional space. Okay. So we can do this. So let's say that the dimension of the space is M, which is smaller than D. There are essentially two ways in which, well, maybe more, but two main ways in which you can do this. So two ways in which you can, in other words, in order to retain as much information as possible. Okay, and the first one is the first one is saying, okay, probably this direction here is the one having more variance than this direction here. So imagine I rotate this, I just rotate it to this axis, right? And then I keep the axis having the largest variance. This is the one we're following here. Maximizing variance. And two, you can also do is to so there are two formulations of PCA, all of them. So you can what you can do is to minimize the sum of squared distances of this, right? So you have this point will have a distance to this axis, and I want to just minimize this. So I want to minimize the sum of the squares, sum of the square errors or distances with respect to the projection. But here I'm following the first method. So the formalism is the following. So imagine that. So here following first approach. So the idea here is to go from a d-dimensional space to the m-dimensional space by first defining a coordinate transformation like the following. So I have a point n, let me just call d1 to d of alpha and d ud, where these objects here are just unit basis vectors. So those are the basis vectors. They are also d-dimensional. That define my transformation, and of course these vectors are they are unitary. So let me just write this as I j is just delta ij. Right. So and then what you can do is the following. Let me just take this expression here, and by taking this expression here, I multiply. So this expression may be called I don't know 1. So I multiply 1 by let me multiply 1 by uj from the right. And if I do this, I get, if I do this in both sides, I get that alpha nj is equal to xn transpose times uj, right? Because I am using the this condition, right? And by doing this, I can just re-express 1 as the following: xn is equal to, I'm just substituting now the expression for alpha nj, d1 to d of nt u d times ud. Okay. This, in a way, this expression is just summarizing summarizing 1 and together with this condition. Okay, so I have this expression on the one hand, and I am interested in a subspace of dimension m, and then I will approximate. In order to do that, I will approximate this is going to be approximated by, let me just put a vector tilde here, which is the following: sum from I1 to m, so the first m components, and I, u, I, and then the rest of it is going to be another thing from k equal m plus 1 to d of some coefficients bk and uk. And because this second part here doesn't depend on the particular point, doesn't depend on n, this is a particular point in of your data set, then obviously this is an approximation to this, right? Of course, I can do a splitting here as well, but in my splitting, the second term for the rest of the dimensions, they will also depend on n. But here, this is not the case. So that's why this is an approximation to the previous expression. And then once I propose this, I decide, so let's decide for a cost function. And the cost function here is written like the following: is just the average of the following quantity, which is n minus its approximation. So I have parameters here, which is my parameters are these, the Z and I, the basis vectors, and also BK. Those are my parameters with respect to which I need to minimize this cost function. Okay, so this minimize it with respect to Z and I, BK, and UI. So since this may be let's say boring algebra here, but I'm just giving you the result of that. So just taking this expression, plugging it here, and differentiate it, see, with respect to all these parameters, you have on the one hand the derivative of the cost function with respect to Z and J. This is equal to 0. This is what we want. And this, by doing this, one gets that the optimum Z and J is equal to this for J from 1 to M, right? So this is the first minimization. I am not doing it here because it is really 3 lines and it's probably not worthy at this point. And if I do similar exercise with respect to Bj, compute the derivative equal to 0, and then the result of that is that Bj, the optimum Bj, is the average of Z transpose, X transpose times Uj, where J is M plus 1 and D. Of course, the BK coefficients, they live in the other, the rest of the dimensionality that we want to discard. So here, that's why J here runs over all these dimensions that we want to just to get rid of. So if I substitute this expression and this expression inside my cost function, then I get, so let me just put, for the sake of clarity, if you see these lectures later, so let me put this, I don't know, this is expression 3 and expression 4. So if I substitute three and 4, if I not substitute, if I plug 3 and 4 inside 2, let me just call this 2 in 2, and then I get something which is C equal 1 over n sum over n sum over I from n plus 1 to d of xn transpose I minus the mean of x transpose times the same square. And by manipulating this even more, what I found at the end of the day is the following. So this is just the sum from I n plus 1 to d of ui transpose times covariance matrix that whose expression I am giving now. So here covariance matrix here is just 1 over n sum over n of xn minus xn times the same thing transposed. Definition of a covariance matrix, right? Of a sample covariance matrix, if you want. So by doing this, we have arrived to an interesting expression here, which is telling you that that this let's say that the minimization problem is all about the covariance matrix of your data. So let us compute at this point minimization of let me write this in black. With respect to the vectors, and by doing this, actually, well, if you minimize this with respect to the vectors, what you get is that the vectors that minimize this expression is that the vectors are 0, and this is obviously the trivial solution, but this is not a solution that is useful for you. So instead, what one should minimize is actually C plus some, I don't know, Lagrange multiplier here. And the Lagrange multiplier is just this. And these lambdas are the Lagrange multipliers of 1. So I'm just ensuring that this condition is obeyed. And now I do minimize C tilde with respect to UI. And the result of this is that S times UI is equal to lambda I UI. So the conclusion is the following. The conclusion is that these basis vectors UI are actually the eigenvectors of your covariance matrix. And now you have a nice way to do it, because the covariance matrix you can compute it is immediate, and by diagonalizing your covariance matrix, you are able to get the basis vectors defining the transformation that you want. Is there any questions so far? Now, S is the dimension of S is what? It's d by d, right? Because original data set has d dimensions, so the covariance matrix has also is d by d consequently. So what we would like is to find the minimum of the cost function. What we would like is to actually choose the d minus m eigenvectors given the smallest given the smallest eigenvalues of S. I need the eigenvectors given the smallest eigenvalues of S because I need these lambdas to be as small as possible, right? And so how we do this? So the general procedure in PCA is to extract, if you want, is to do the opposite actually. So what you do is to sort, if you want, diagonalize S and sort the eigenvalues, extract the eigenvectors, and then you keep, so the m dimensions to keep are going to be those defined by the these eigenvectors. Okay, so this is the generic procedure to go. Any question? Okay, so then the idea is just that. So the new variables, the new data set or the new variables are given by, for a given point n in the data set, are given by the matrix U. So this is the matrix of this is the R matrix, or the matrix that diagonalizes, if you want, the covariance matrix, or the combination of all eigenvectors here, times xn, and actually multiply by something here, which I will define in a moment. So just to tell you that this U is just U1, U2, Um, right? I mean, the dimensionality of U is just D by M. So this is like a rectangular matrix. And L is just is such that, well, you have that U T S U is equal to L, right? So L is just the diagonal matrix resulting from the diagonalization. And the only reason we do this, we include this term here, is just because you are ensuring that this transformation, these values, which are called, these directions, which are called the principal components, the principal components here will have unit variance. They have unit variance. And it is easy to see this. So let me just compute the covariance of that. So this is just the unbiased covariance here. That's why I have this 1 over n minus 1 of n, yn times yn transpose. And this is just 1 over n minus 1. I'm just replacing here L minus 1 half ut xn n transpose u L I minus 1. So this is just L minus 1 half ut s u L minus 1 half. And by definition, this is 1. Because this guy here, I told you that is L, right? So the covariance matrix of these principal components, or the transform variables, or if you want the transform points, are have covariance 1. And that's it. So the idea here is to say, okay, how many components I would like to keep? How many components to keep? I mean, what is the value? What is the value of M? Again, here this is just a question of domain, but there are some recipes in the literature for that. A reasonable one is to put a lower cutoff on the components of the eigenvalues. For example, one recipe just keep the eigenvalues of your covariance matrix that have that are larger than 1. This is actually for standardized data, okay? Once original data is standardized, I mean, having zero mean and unit variance. This is called, I think this is called the Kaiser rule. And it's quite popular among the PCA practitioners. So the idea behind this rule is simple. It's just that if all the original variables were independent, then, so for example, I'm imagining a situation like this. Imagine I have no correlation at all in my data set. This is just that. Then, so as a result, the PCAs, the principal components, so we'll have the same, remain the same, right? They remain as the original. Because essentially there is no preferred direction here. So you, with a data like this, you can say, okay, this cannot be reduced. And then since I have started with the standardized data, here this will have unit variance. And since I have unit variance, the lambdas are going to be 1. Because I have unit variance and lambda is the eigenvalue of the covariance matrix. So in a way, the Kaiser rule, what is trying to implement is the fact that, okay, let us first standardize the data and keep only those directions for which I have eigenvalues larger or equal 1. But it is not the, by all means, it's not the only recipe. There are many of them, and there is a whole literature on that. But this is more or less the idea of PCA. Is there any question so far? At least about the philosophy of PCA. Is there any doubt or something? Okay, so if not, I think we are done for good. There is no homework in this lecture. I don't want to be pushy, and there is only 2 days left for the deadline, so I don't want to make some pressure, more pressure on you. So yeah. Any question about this? Yes.
No, I have a question about the homework.
Yeah.
The notebooks that we are supposed to play with different parameters. How do you want them to be sent? Like the notebook with chase parameters or some plots, or how can we?
Just send me the notebook, no?
With different parameters to show things, that
Yeah,
we are.
you just show your exercise is probably done in a notebook, and then you just show in this notebook. You just show the different parameters, the result. So it's an illustrative way of and informative also to share your results, because I know what you have been doing. Otherwise, if you just send me plots, then I don't know how you get it, how you got these plots.
Okay.
All right, so let us close this course, and then thanks for being till the end. I don't know how many of you are. Okay, 1/3 of the initial people registered is not bad. 1/4. Okay.
Thank
So
you so
would be
much
great.
for the course. Yeah,
Thanks to you guys.
Yeah, thank you.
Thanks. So bye bye.
Yeah, thank you.
Thanks.
bye.